This is Physical Science 2, Chapter 26, Part 2 on stars and galaxies. In this portion of the video lecture, we will be discussing the evolution of stars. Since we have all of these bright glowing balls of gas out in space, where do they come from? Stellar evolution starts in what we call a nebula. A nebula in space is a very large cloud of ice and gas and dust particles. And as those ice and gas and dust particles become closer to each other, they have more gravitational attraction. They will attract more ice, gas, and dust particles the larger they get. And we can kind of fast forward this nebula from a large cloud to kind of a protostar, or kind of a very newly born star from a nebula. Two very important astronomers, Enyar Hertzsprung and Henry Russell, were classifying stars and cataloging stars. And they were comparing the brightness or the luminosity of stars versus their surface temperature. And as they were charting these stars, comparing luminosity and surface temperature, they realized that stars kind of ended up in these certain types of categories. And so they developed what's called the Hertzsprung-Russell diagram, which, as you can see here, gives us along the x-axis, or the horizontal axis, gives you the temperature of the stars, the surface temperature in degrees Kelvin. So the x-axis is a little bit backwards here. 30,000 degrees Kelvin is much, much, much hotter than 3,000 degrees Kelvin. So increasing temperatures and decreasing temperatures kind of split from the middle of that x-axis. And then on the y-axis, we have the luminosity, or the brightness of stars. And so we can take the surface temperature of a star and associate it with its luminosity, and vice versa. The hotter a star is, the brighter it will be, and the cooler a star is, the darker it will appear. So again, we measure star temperatures in degrees Kelvin. 273 degrees Kelvin is equal to 0 degrees Celsius. It's just another metric type unit that we use for star temperatures. Colors associate with those surface temperatures. A very red star is kind of on the cooler side. Our sun is yellow because it is kind of your average Joe temperature surface-wise, so it's kind of a warm star. Blue stars are very hot, and we consider white stars extremely hot. So once we get from the nebula, that large cloud of ice and gas and dust, to a protostar, how do these stars change throughout their life cycle if they were living things? A star needs to maintain what's called stellar equilibrium. Stellar equilibrium is a balance between two forces in a star. The fusion forces, which are the inside force of a star, and gravity is the outside force in a star. So fusion works from the inside and pushes the star out, whereas gravity works from the outside and wants to push the star in. So when a star, after it becomes a protostar, it will undergo stellar equilibrium. And it will form into what we call a main sequence star. So this is when a star's gravity equals fusion. So stellar equilibrium is maintained. Just about all of the stars that we have cataloged fall into this main sequence star category. Now, most of space is made up of hydrogen and helium, and if you consider kind of the starting fuel in a star is hydrogen gas. And what main sequence stars do is they convert hydrogen gas into helium gas by fusing hydrogen atoms together. So when hydrogen atoms bang together, we get a lot of energy, for one, heat and light. And as long as, again, that gravity and fusion are equal, a main sequence star will happily convert hydrogen gas into helium. Now, eventually, all of the hydrogen gas will eventually get used up. After this happens, then stellar equilibrium is thrown off a little bit, because now what will happen is the fusion energy that pushes from the inside out of the star will start to lose over gravity, which is pushing from the outside in. So the core of the star will contract due to gravity, and there will be an increase in that core temperature. So what will happen is the outer layers of gas from a star that are far away from the core will start to expand and cool off as they diffuse back into space. Now, those gas particles will become a nebula at some other point to start and generate another star. But after all of the hydrogen is gone, a star expands and becomes what we call a giant star. So this is kind of the later stages of a star's life. Depending on the original size of the nebula, we can also get super giant stars if they come from very large nebulas. So the core continues to contract, the temperature will increase, and then at around 100 million degrees Kelvin temperature, what will happen is that helium, which is now a new kind of starting fuel for a giant star, helium atoms will fuse together to form carbon atoms. Now, that's important for you and I because we, along with all other life on this planet, is carbon-based. Basically, every single atom of carbon in your body was at one time fused in a star. So as our giant star continues to grow, the outer layers of gas escape and drift off into outer space. And that hot, dense core sticks around and it will continue to contract. So now it becomes what we know as a white dwarf. White dwarfs are kind of like the retirement stage for main sequence stars. White dwarfs are very small stars, but they are very, very hot, indicated by that white label of their color. So the only thing that a white dwarf is a really tiny, hot, small star. Eventually that temperature will raise inside that core, and we can take carbon atoms and fuse those together to form oxygen atoms. Again, something that's important to you and me and all life on the planet in some way, shape, or form. In super mega massive stars, stars that are 8 to 25 times larger than our own sun, this fusion process will continue, and oxygen atoms will fuse together to form neon atoms. And we can get neon atoms forming into other heavier elements. For very large, super heavy cored stars, supergiant stars make heavier elements. The bigger, the fatter the star, the bigger, the fatter the elements that can be made. So neon atoms on megamassive stars fuse to form magnesium, which is one of the important biological salts. Magnesium can fuse to form silicon. Silicon can fuse to form iron. And we can keep this process going. So all of the materials in the universe are made and generated by stars. Eventually, in some cases, the core can get so very heavy due to gravity, and it gets squeezed so tight that the core of a star will actually collapse on itself. And that will cause what's called a supernova or a nova, which is when a star literally explodes. What remnants of what is left after the supernova from very mega massive stars is what we call a neutron star. A neutron star are the smallest stars, but they are the most dense because that core is so jam-packed of matter. It is very, very dense. And in some cases, very, very large stars can even collapse past the neutron star stage and form what we call a black hole. Black hole, these are believed to be so strong that nothing, not even light, can escape a black hole. There are a lot of theories about where these things are in space. When you think, how can you find a black hole in space since your basic space color is black and your black holes are black? How do you find something black on a black background? Well, you observe weirdness, basically, when stars or objects behave abnormally in our view. When we track movements, that can indicate kind of weirdness, can indicate a presence of a black hole. So type 1 stars. Type 1 stars are like our sun. They're hydrogen poor, they're kind of low mass, smaller stars. They'll end up their life as a white dwarf. Type 2 supernova stars. These are the big guys. These are hydrogen rich, very high mass stars. The end of their life will either be a neutron star, or if they are a mega massive star, they'll end up their life as a black hole. Now we'll talk about our own star that's very close to us, the sun. It is a main sequence star, so it is happily churning away hydrogen atoms into helium atoms. But by studying the surface of the sun, that can give us clues to what's going on in the interior of the sun. We call the surface of the sun the photosphere. Photo in Latin means light. So this is the surface of the sun that actually gives light, and it's around 5,000 to 7,000 degrees Kelvin. Even though the sun is not a planet, it does have an atmosphere. The atmosphere above the photosphere is composed of 2 layers. The first is called the chromosphere, and the second layer of atmosphere is called the corona. And the corona is what we observe during a total solar eclipse. So, going structural wise, from the inside out of all stars, including our sun, the core, that's the innermost layer, so that's where fusion is occurring. That's where the hydrogen atoms are banging together to form helium atoms. That process generates a lot of heat and light. So the radiation zone is above the core, so that's where the heat is generated. And then above the radiation zone, we have what's called the convection zone, where heat energy travels in a circular motion on its way out to space. So the surface of the sun, when we look at it through specialized telescopes, of course, so we don't go blind, we can see that the sun has kind of a mottled appearance. We call it granulation. It's kind of very similar to if you're looking at embers in a campfire, that kind of glowing chunks is what the surface appears to look like. There are some instances on the sun where we have some interesting things going on. Sunspots. These are cooler and darker than surrounding areas of the sun's surface. They're associated with magnetic fields. They can appear and disappear over a period of days or weeks or months. About every 11 years, we hit the sunspot cycle. So kind of a maximum amount of sunspots happens about every 11 years. And again, this has to do with the sun's magnetic field, which is a little more wonky than the Earth's magnetic field because the sun is a giant ball of gas. Some other instances of things coming from the sun, a prominence. These are huge arching columns of gas that come from the interior of the sun. Again, they're associated with sunspots. So the more sunspots you have, the more prominences you would have. Solar flares are another type of phenomenon on the sun. Solar flares are kind of a one-port shootout. So when sunspots brighten subtly and shoot out gas at a high speed, that's what we call a solar flare. Now, when there's a minimum amount of sunspots, we have what are called coronal mass ejections. These are kind of when the sun kind of bubbles up some ionized gas. These will increase the solar winds, and so CMEs can be dangerous if we didn't have our magnetic field protecting us. And these occur during sunspot minimums. So this has been Physical Science 2, Chapter 26, Part 2 on stars and galaxies.